Peter, suppose you want to find the volume of a sphere. How would you set up the integral?
I just use 4/3 pi r cubed. Everyone knows that.
Yes, but where does that formula come from? We need a triple integral over the sphere's volume. Here's our sphere. Radius r. We need to integrate over every point inside. In Cartesian coordinates, the integral looks like this. 3 nested square roots. Absolutely monstrous.
Holy crap, that's uglier than my cousin's wedding photos.
The problem is the spherical boundary. Each bound depends on the outer variables through those square roots. It's a nightmare to evaluate.
Can't we just use different coordinates like we did for the cylinder?
Precisely. We use spherical coordinates. Instead of x, y, z, we use rho, theta, and phi. Rho is the distance from the origin. Theta is the azimuthal angle around the z-axis. And phi is the polar angle down from the z-axis.
So rho tells you how far out you are, and the two angles tell you which direction.
Exactly. For a sphere centered at the origin, the bounds become trivially simple. Rho goes from 0 to r, theta from 0 to 2 pi, phi from 0 to pi. The integral is now beautiful. But wait, there's that extra rho squared sine phi in there.
Where'd that come from? Did you make a typo?
That's the Jacobian. When you change coordinates, you must account for how the volume element transforms. Here's what the spherical volume element looks like. It's a curvy little box bounded by constant rho, theta, and phi surfaces. Think geometrically. The radial direction contributes to rho. The polar r contributes to rho d phi. And the azimuthal r contributes to rho sine phi d theta.
So the arcs get bigger as you move outward and toward the equator?
Precisely. The rho squared comes from the two angular arcs scaling with radius. The sine phi accounts for circles getting smaller near the poles. Remember, dx dy dz equals rho squared sine phi d rho d phi d theta. That Jacobian is non-negotiable. And solving our sphere integral? It evaluates to 4/3 pi r cubed, the classic formula derived rigorously.
So spherical coordinates are like the cheat code for round stuff?
Exactly. Match your coordinates to your geometry. Spheres, cones, anything with radial symmetry. Follow for more.